Okay, so let's get started. So this is computational phases of quantum matter still. So I think I'll review our review from last time about matrix product states at the beginning. So just to make sure that we kind of are on good terms with that. Then I briefly talk about group cohomology, which is used in the classification of symmetry-protected topological phases. And then talk about computational phases of quantum matter. And there will be a first part about just wire, symmetry-protected measurement-based wire, and then I will talk about computation. So that's the plan for today, and that's about 50 slides, and I have no idea how to get through them. Okay, so here is your reading suggestions. So the first paper by Groß and Eisert is about measurement-based quantum computation in the MPS framework. Second is a very easy and kind of colloquial introduction to group cohomology. So that's the subject, a mathematical subject that we will touch today, not at any greater depth, but so if here you find more than I'm able to explain today, but really not more than necessary. So there will be a homework about this whole area, and I think this paper may help you with the homework if anything is missing. Okay, so I strongly suggest it. Then the third paper is about the third part of this lecture, about symmetry-protected wire. This is a paper from the University of Sydney, and we will review it here. And then this is a paper from our group about computation. Okay, so this is your reading suggestions for today. Yeah, so let me recap what the motivation was for this whole idea of computational phases of matter. And the question is really, can MBQC resource states be classified? Okay, and so kind of one reference point for this whole endeavor was this paper by Groß, Flammier, and Eisert in 2009, who showed if you choose randomly from Hilbert space, then, well, at least with overwhelming probability, you'll find a useless resource state, or a quantum state that's useless as a resource. Maybe the useful states are even of measure zero, we don't know, but we can say with overwhelming majority, with overwhelming probability, 1 minus epsilon, you find something useless. So MBQC resource states are rare, and that justifies their classification. Yeah? So if you pick something random, it will not be useful. Okay, so this was one reference point, and here comes another. So then maybe you think that resource states are kind of like isolated points in Hilbert space, separated from one another, but that's also not true. And the first indication about that came from Andrew Darmawan and collaborators, also from Sydney, same group. And they figured out that around the AKLT state, the two-dimensional AKLT state, there is an entire phase, or a one parameter family of quantum states that have all the same universal computational power. And physics-wise, this phase comes to an end at a certain point, that was previously figured out. And the computational power vanishes precisely at the same point. Okay, so this was the first indication for these computational phases of quantum matter. And kind of the formalism was put in place by Akimasa Miyak. And he realized that this is all connected to symmetry-protected topological order. We talked about that paper last time. Good, and so now here is the result to establish. We want to show that computational power is uniform across phases with symmetry. Yeah? And uniformity of computational power is the property that defines this notion of computational phase. Part 1, review of matrix product states. And I think I want to be fast, but you can interrupt me at any time. Yeah? So we discussed this last time. So this whole MPS business is about writing quantum states in a certain form. So here you have a basis expansion for your states in a Hilbert space of a given dimension. So the local dimension is little d, and so the Hilbert space dimension of this whole thing is d to the n, small d to the n. Okay, and so you have expansion coefficients when you expand in this basis, and you write these expansion coefficients in this form. Yeah, so you have a bunch of matrices like so, and you multiply them together and then maybe attach boundary conditions to contract the remaining indices. And you can, in fact, so this is a general representation. You can write every quantum state in this form. There's no restriction. But the question is, how large are these matrices? So these matrices are by assumption d by d. And how large is this parameter d? Now, if you make it large enough, you can represent any quantum state. But what can you represent with small d? Fixed dimension. Yeah, and it turns out physics-wise, you don't need to go that far. So quantum states that are of interest for condensed matter physicists, they typically get by with small values of d, or can at least be approximated with good accuracy with small values of d. And once you have that property, then you can efficiently represent quantum states in this framework. Yeah? Because it's just, I mean, the number of coefficients you need is polynomial in anything, then, yeah? In the number of particles, dimensions, and so on and so forth. So this is good. This cannot be particularly useful for general quantum states, but for quantum states that occur in physics, it's actually a good representation, a good and efficient representation. Okay, so this formula written graphically looks like this. So we have a bunch of tensors. So their so-called virtual legs are being contracted. So this tensor leg contraction is matrix multiplication. Yeah, and so you have legs sticking out. These are for these indices here, and they represent the physical system. So that formula in graphical notation looks like this. And from this point, we can explain measurement-based quantum computation quite well. But maybe the first thing to say is that a quantum state is now represented by this local object here. Yeah, even though it's an entangled state, you can represent it by a local object. Okay, and so now we can think about measurement-based quantum computation like this. So you have the tensor, you measure. A measure is represented by contraction with a tensor like this. Yeah, so the bra representing the measurement is a one-leg tensor. You contract, and so this leg disappears, and you have now a two-legged object which is a matrix. Yeah? And so you are performing a transformation on this virtual space in and out. And so now these transformations, well, if you're clever, they can be chosen unitary, and then you can view your measurement-based quantum computation in this way. So they get simulated are these tensor components. Okay, good. Now, of course, a few questions arise. So you have to ask yourself, for which post-measurement states are these indeed unitary, if you want to implement unitary evolution, and then furthermore, for which bases are these operations unitary for all states in the basis, in the measurement basis, okay? And that it doesn't stop there. You need even more than that. Okay, but just to point out to you that you have further constraints, and these constraints, they constrain the bases in which you want to measure. Maybe the overall picture is more important, so this is what happens. So here you have your state, you're contracting through measurement of these particles, and then these tensors with one leg contracted are transformations, and so your logical state, the quantum register, lives on this virtual system, and it's hopping from time step to time step to time step, being processed by these matrices. So that's the picture. Okay, and so now you can do this for various states, And so here it is for the cluster state. And I think this is on the homework assignment. So you will prove what I now say. So for the cluster state, so maybe let's go back to when I introduced this MPS formula. So I wrote this in a specific basis. And that basis you can choose to your liking for certain reasons that maybe become clear later. For the cluster state, it is useful to choose this the X basis. So all these states are eigenstates of the local operators X, not Z. So the X basis is preferred for our expansion because if you choose that basis, then all your matrices will be unitary. Remember, that's something we wanted. Okay, and this is what they are like. So, so these signs here indicate the eigenvalue of X for the state in the expansion. So, oh, sorry, I should also say we are blocking the sides. We are not looking at one side at a time, but a pair. And the reason we do that is, remember when we described MBQC in terms of the circuit model earlier, so going from one side to the next, we have a Hadamard transformation. And so when we go from one side to the second next, we have two Hadamards which give the identity. And that picture is what we like here. So we are bunching sides together, and that's why these matrices now have two labels. Yeah, a label for the side n, say, and side n plus 1. Okay, and so for both labels plus, you get the identity, and then with these various sign combinations, you get the other Pauli operators. So that matrix A, whatever the labels are, is a Pauli operator. Also, I mean, this subject is all about symmetry, and so it is worth pointing out that to say that the cluster state has a symmetry of type, if you look at the group structures, a Z2 cross Z2 symmetry. So every Z2 has two elements, the identity and the non-identity element, and the product of two such group has 4 elements. Okay, and yeah, so to each of the non-trivial elements in either of these groups, you can assign a generator of the symmetry. So the non-trivial element in the first Z2 gives you this generator, and the non-trivial element here gives you that generator. Yeah? So if you act on a cluster state with these operations, you get the cluster state back. And maybe you can see that. So this operator is a product of stabilizer generators. Remember, stabilizer generators are from ZXZ. Now, if you multiply them together, Z's cancel in the middle. So these are elements of the stabilizer, this guy and that guy. So it turns out that near the cluster state, there's other quantum states that are not stabilizer states. They do not share the cluster stabilizer, but they are still states that are invariant under the symmetry. And that is states of our interest. So today, I mean, whenever we're looking for an example, we will be looking at this example. States that are near the cluster state, but not exactly cluster states, but they still share that symmetry with the cluster state. How do you get that state? Maybe I should talk about that briefly. So, so let's consider some Hamiltonian for a chain. So I don't know, from 1 to, so I'm not fretting about permit me to not fret about the boundary right now. And it's easier to write. So our Hamiltonian, so we have a coupling constant is minus Zi minus 1 xi Zi plus 1. Okay. So so we can ask for the ground state of that Hamiltonian, well, that's a cluster state. Yeah? So the terms in the Hamiltonian are pairwise commuting. So the ground state is the simultaneous eigenstate of these operators with eigenvalue +1, because of the minus in front. And that's the cluster state by definition. So, but now let's say you have a whole family of states. So yeah. So add a local magnetic field in the x direction. And then you get a one-dimensional phase diagram. So what could you plot, for example? Let me see. You could maybe plot a stabilizer. What do we want to plot? Yeah, I think you can plot something like this. Okay, and on this axis we have this ratio. Let me do this differently. Let me do the parameterization like this. We have minus g cosine alpha, and here we have minus g sine alpha. So when alpha is small or 0, this term plays no role, and we have the cluster state. When alpha equals pi/2, then this plays no role. We only have the magnetic field, so at that point the ground state is a product state. Okay? So this is alpha now. This is pi/2. So this is a product state here. This is the cluster here, so it's 0. So this is the cluster state. Yeah, and you can see that this expectation value changes as alpha varies, and at the point of alpha equals pi/4, you have a phase transition. And so the cluster expectation value disappears. Okay, long story short, why am I introducing this model? Because the states here all along have this symmetry. Yeah? But there's two phases, a cluster phase and a trivial phase. And later we will be talking about both the classification of these phases and measurement-based quantum computation in these phases. So it turns out MBQC is possible all throughout the cluster phase until this right to this transition point, and it's not possible in the trivial phase. And computational power is uniform here. You can do the same regardless the value of alpha, as long as you're here in this phase. So that's an example for kind of a set of quantum states that have these symmetries. And that's what we want to talk about today. Oh yeah, what does it act on? So these are spin 1/2 particles. So that is what the symmetry acts on. And these are Pauli operators. This is the generator for the first Z2. And this is the generator for the other Z2. And you see the two are independent because of the displacement. And exactly. So we are bunching these sites together. And the property that we are getting out of that is that the symmetry, what's it called? Is that truthful, faithful? Yeah. So the action of the group is faithful on the block. Yeah. There's no symmetry element that acts as the identity. And that wouldn't be true if you had just a single site. Okay, but you have this periodic repeating pattern in which the symmetries act. Let's move on then. Okay, so that was all I wanted to say about the MPS formalism, the setting, and so forth. Okay, so now let's talk about group cohomology a little bit. Okay, so this is a result that I will not prove to you today, but at least I want to explain what the statement means. So the result says that in spatial dimension 1, that is spin chains, the symmetry protected topological phases are characterized by the symmetry group that applies, let's call it G, and the corresponding cocycle class, omega in angular brackets. Yeah, it's an element of the second cohomology group of the group G. Okay, so I'm not proving this fact to you. So there's a bunch of papers about it. So here you see two. And if you're interested in their classification, I recommend those papers to you. So for us today, it shall suffice to parse the statement. Yeah? So we have a mathematical classification of these phases. Yeah? So this is all that has to do with symmetry. A symmetry is present, and so it turns out in spatial dimension 1 that the classification is in terms of that symmetry. That's not so surprising, but the object that does the classification in the end is this cocycle thing. And so we want to talk about what that is, because that will become important for the MBQC part as well. To define a cocycle, we have to define cocycle and cocycle class later, but before we can do that, we have to define another object, and that's the projective representation. Cocycles, and you see them coming up here, they will be properties of projective representations. So what is a projective representation of a group? A projective representation is approximately a representation, but not quite. So in a representation, a group, a linear representation of a group, this factor omega would always be 1. Yeah? Think of this factor not being there. If this factor is 1, then what you have here, V, would be a linear representation of your group. That's the property that defines it. Okay, but the factor is there. It is not necessarily 1. So you do not have a representation. So that thing with this face sitting there is called a projective representation. And the projective representations we want to classify. Yeah? So these are factors in U1, yeah? Just angles exponentiated. Okay, and so, so why does this thing come up? So, so it turns out, and that's the fundamental relation, that's also something that you will find in one of these papers. I will not prove it here, but that's the starting point of the whole analysis. So it turns out when you have a state, or ground state of a system invariant under a symmetry, yeah? So I should say, maybe I should write that down. So what we have here, so we have a quantum state that we are interested in, and it is invariant under the symmetry. And so now the symmetry is acting on all the sides. Yeah. Okay, so in our case, pairs of sides. Okay. So, and this is supposed to hold for all G in the symmetry group. Okay, so what we have here, so this is an invariance condition. The state phi is symmetric under something. And so Ui of G, so this is a representation of the symmetry group. a linear representation now. And well, there's one such thing for each site or block in the lattice, and then you take the tensor product of that stuff, and that's how the symmetry acts on the whole system. Okay, and it's a symmetry transformation, so it leaves the state invariant. Okay, so that is the states we care about. So, and it turns out, at least in the limit of infinite systems, when you have that, then you can describe your states, your state phi, always by a tensor like so, that has this invariance property. So from the invariance property of the state follows an invariance property of the tensor. Okay, so that is not easy to prove. I'm not doing it here. But what is easy to prove is the converse. Yeah? So if you start with a tensor that has this symmetry, and it's easy to show that the resulting state has that symmetry. Okay, and because it is so easy to do, let me do it. So this is not the direction that we need, but it shows you that this relation has phenomenological significance. So we said that. Okay, and let me not worry about boundaries right now. So boundaries always complicate. Yeah. Okay, don't want to bother with boundaries. So I'm just joining the boundaries. So this is our state phi in graphical notation. And so now I see that I can use this relation. So I have now I can insert these. Sorry, there's a label G, B of G, a V dagger of G. Okay, now comes the next block, V of G, A, V dagger of G, and it goes on and on and on. Okay, and here we shouldn't forget we have U of G acting. Okay, and so now the point to see is that you have V daggers meeting V's. And since these are unitary, they cancel each other out. Yeah? And so this happens everywhere here. So they always appear in pairs. And so all these VV dagger pairs cancel, and what you're left with is these linear representations acting on the physical legs. So this is indeed the graphical representation for symmetry operation acting on the state. Okay, so that was the easy part, going from this relation. Yeah, so the symmetry of the tensor implies the symmetry of the state. That's the easy thing to do, but the other direction is more complicated. Good, and I'm not proving that here. I'm just stating it as a fact. And so now, so the interesting thing is there can various representations, various projective representation can appear in this invariance condition of the MPS tensor. And so there's now a property of this projective representation that tells you which phase you are in. Yeah, and that has to do with this phase over here. Okay. Okay, so something about the phase over here will tell you what phase you are in. And now these phases here are subject to a constraint and an identification. So first to the constraint. Yeah, so these phases, I mean, they cannot be arbitrary. So Yeah, they depend on two group elements. And yeah, there's consistency conditions among those. So the first comes from the associativity of multiplication. So these projective representations, they are matrices, and matrices are associative under multiplication. So I can, when I have this triple product here, I can decide to first multiply the first two and then multiply on the third, or I can decide to first multiply the second and the third and then multiply the first from the left. Yeah? By associativity, this must give the same, and that has an implication for what these factors can be. So there will be a constraint coming from that. Okay, so that is the constraint. And there is an identification too. So there will be sets of phases, omega, or phase factors, that we consider equivalent. And that comes from this condition over here. So let me first state it and then explain why we impose this equivalence. Okay, so let's look. So let's look what's happening here. So we take an element from the representation and multiply it by some phase factor. Yeah, it can be different phase for every group element. So we regard this as equivalent. So we are saying, okay, we can do that, but nothing's really happening here. And why is this? So for that, let's go back to this picture here. So suppose we multiply V of G with some phase factor. So then you see here on the other side, the Hermitian edgine of V occurs. And so then it will have the complex conjugated phase factor over here. And the former phase factor and the complex conjugate will cancel each other out. And so under this transformation, the symmetry condition remains the same. And so in that sense, the phases we put there have no effect. Okay, so that's the identification. And this constraint and that identification make this thing a co-cycle equivalence class, which is an element of the cohomology group, second cohomology group of the group G. Okay, good. I want to spell that out a little bit more. I have a slide about the constraint, a slide about the identification, and so on and so forth. So let's get started. So let's take this apart a little bit. Okay, unfortunately, well, fortunately or unfortunately, I changed my notation here a little bit. But anyway, let's first talk about the constraint. So the constraint comes from associativity of multiplication. So what I have changed here is I changed this prefactor omega into e to I times some angle. And the reason is, rather than multiplicative expressions for these factors, I wanted additive notation. That's why I did it. Yeah. Okay, so you work it out. Yeah, you do the products both ways. You plug in these expressions, and you find a combination of four such phases. Yeah, so remember, each phase has as arguments two group elements. Yeah, and yeah, so yeah. And because of these successive products that you form, you get these various phases, and you get a linear combination of such phases that will add up to 0 mod 2 pi. And that's that constraint. And in cochain notation, yeah, so there's a whole formalism if you want to get more formal, and this group cohomology paper will explain you all about it. Yeah, you can write this as the coboundary of these phases phi equals 0. So it just matches the definition of the coboundary operator for these objects. So This phases phi are so-called two cochains in group cohomology, and that just means they are functions that take as arguments two group elements. Yeah? So two group elements is for the two here, yeah, cochain because we are dealing with functions on chains. Okay, it's a two cochain, but the two cochain satisfies the condition that its co-boundary is 0. And because of that, and again, that's just a definition, this is called a two co-cycle. So our phases in group cohomological terms are co-cycles, two co-cycles. Okay, so that's the constraint. So again, sorry, I'm switching my notation a little bit. So this whole thing was previously called chi, and now I'm writing it again as e to the I times a phase because I want that additive notation. So what's happening is that the projective representation now for every element acquires a particular phase. And it can be anything. So this is kind of like a gauge transformation. Again, I mean, the physics, that transformation doesn't change the physics, and we have already explained why. If I make this transformation, the constraints on my tensor remain exactly the same. So the tensors that will result from that constraint will not change. Okay, so that's the reason why. Okay, and so now the question is, if I make this transformation, what happens to the former phase phi that was governing this multiplication rule? So that phase will not stay the same. So if you plug in all that stuff here, you find that this phase phi changes as follows. So it basically remains what it was, but it receives an offset. Yeah, so we have these phases alpha for the various group elements that are involved, namely G and H, and the product. And again, in group cohomological terms, this combination here has a name, and that's a co-boundary. Yeah, so alpha is a one cochain because alpha depends on one group element only. Yeah, it's a function on the group that makes it a cochain, and it depends on one group element only. So that means it's a one cochain. Okay, and so alpha is a one cochain, and so this means that d alpha, co-boundary of alpha, is a two co-boundary. Yeah, so d alpha depends now on two group elements. Yeah, so that makes it a two cochain, but it is a two cochain of a very special form, namely it is a co-boundary. Good. Okay. So that was the identification. Now comes the quotient. So remember, our cochains, they had the phis had the property that if we take the co-boundary of it, that gives 0. So now it turns out that if I take the co-boundary of d alpha, so that is also 0. I can explicitly check that. And therefore, if I'm making this transformation, yeah, so the transformation we looked at, we take the phases that we had and subtract this co-boundary, then this co-cycle condition is preserved. Yeah. Okay, physics-wise, we are not changing anything, and so what we really care about is the equivalence classes of those functions phi under adding or subtracting these co-boundaries. Yeah? So yeah, physics-wise, it was just a canceling of phases condition, and mathematically, this is what it turns out to be. So we have a two co-cycle here, and we are free to add any co-boundary that will physically have no effect. So this is now the cocycle classes we care about. So on previous slides, they were called angular bracket of omega, but remember, this is the same thing. This is just additive notation. Yeah, so the phi's and the omegas are related by omega is e to the I phi. So let's collect these facts now from a mathematical perspective. So the phases phi, so these are functions now that take two group elements and map them into, oh dear. I shouldn't say U1 because I was so insistent on my additive notation. So maybe I should rather say, so this is R mod 2 pi. Oh, maybe that is U1. So the thing is, though, that, okay, phases that satisfy the consistency condition d phi equals 0, they form a group. So suppose I have one such set of phases or one such function, and I have also another such function, then the sum and the difference of those, they will also satisfy this condition. Yeah? And so I have a group structure here. So the functions phi that satisfy these conditions, they form a group. And we denote it like this. This is not a z squared or something. This is just the name of the group. Z is the group of cocycles. And the upper label 2 indicates here that's the group of two cocycles. So there's various cocycles around, various such solutions of this equation for phi. And these various solutions form a group. And that's that group. Okay. And then there's another group around here that's called B superscript 2. That is the group of two co-boundaries. Yeah? So that is the D alpha that we previously had. So they also, so if you let alpha vary, so we remember we could have a different angle alpha for every group element. And so this function alpha going from the group to the real numbers mod 2 pi. So these functions have a group structure, namely if you have one such function and another, and then you add them, that is also a co-boundary. Okay, good. And so now what we are interested in these equivalence classes is the cocycles modulo the co-boundary. So the co-boundaries is what we are quotienting out from the cocycles, and this quotient is called the cohomology group. Yeah, so in our case here with superscript 2, it is the cohomology group at second level. Okay, so that is a group that describes this setting here. And now we wanna know, how many elements does this group have? Yeah, given our symmetry group. So that's now a mathematical exercise to figure out. But each element of that group will correspond to a phase in our SPT phase diagram. So I already stated that result. So in spatial dimension 1, and that's what these people here have proven, the symmetry protected phases are characterized by this cocycle class, omega or phi in additive notation. Okay, so I mean, what are you supposed to get out of all of this? I hope this fact we will not prove here, but what you are supposed to get out of this at this point is that at the bottom of all of this stands this invariance conditions, the invariance condition of the MPS tensor. Yeah? And yeah, so now we are asking ourselves what projective representations can occur here to the left and right. And they are classified by these equivalence classes of group co-cycles. So these objects here are classified by group cohomology, as we just discussed. And that group cohomological formalism will become important for us when we move. I mean, it's interesting for condensed matter physicists because of the classification result, but this group cohomology formalism will also be of interest for us when we talk about computational phases of matter. Symmetry protected quantum wire. So that's that paper. So we saw it last week. So the achievement of this paper is that these people took this group cohomology framework that was already known in condensed matter physics and apply it to quantum information. Yeah, so let's see how they do that. Okay, so this is the result. So consider an SPT phase, symmetry protected topological phase, characterized by a finite abelian symmetry group and a maximally non-commutative cohomology class. Okay, so so I explain in a moment what this is. So it's not a general cohomology class, not just any, but is of a particular type. Then for every matrix product state in this phase, there exists, so sorry, there's maybe a piece missing. So that class, again, defines a phase. And then for every matrix product state in that phase, so here the assumption is that every state in the phase can be described by a matrix product state. Well, every MPS therein, there exists a basis, the symmetry respecting basis, with respect to which the MPS tensor has the following decomposition. So it has a decomposition. Okay, and that decomposition is nice. So this tensor you know already. So these are the components of the MPS tensor. Yeah. So the label I here is because the tensor A has been contracted with a basis state with label I. So that's why. Okay, and so that tensor now has a special form. And that special form will be very, very useful to us as we see shortly. So let me point out to you what's particular about this structure. So you have a tensor product. So it has two parts which are joined in a product. And so one has the label junk, is indeed the label that they use. They call this the junk subsystem. So this operator acting on the junk subsystem. And then you have the logical subsystem. And so you have this logical operator CI sitting there. And both depend on that label I in general. Okay, and so now the CIs that appear here, they have the particular property that they are constant throughout the phase. So you move about in the phase, the state changes, but for the MPS representation, this part of the MPS tensor does not change. It is constant throughout the phase. Okay, and then there's a junk part about which you know nothing. Nothing at all. So it splits into a completely known part. So it's an element of a finite group. They say, and it's constant. So it's perfect in a sense. And then you have another part, about which you cannot tell. Good. So that's what they proved. The physical implication of this is that one can quantum wire on the logical subsystem. And we come to that. I mean, it's kind of obvious, but we will spell it out. But before we get to that, we have to parse a few terms here in the theorem statement. So maximally non-commutative cohomology class. So that's something we have to explain. Maybe symmetry respecting basis is a term that we need to explain. Yeah, and that's probably about it. I think those terms, yeah? So let's begin with maximally non-commutative. And so, yeah, I think I don't need to necessarily write. I can just say it in words. So you have the group elements, and every group element has a projective representation. Yeah, so that's some matrix, some linear operator. And so now now it can happen if you look at these elements of the projective representation, you may wonder what commutes with what. So now you see, obviously the identity, so the projective representation of the identity group element will be proportional to the identity as an operator. And of course, so the identity commutes with everything else. Yeah? And so the question is there something else that commutes with the entire projective representation? If that's not the case, then you're dealing with a maximally non-commutative representation. We can look at an example of that. I mean, in fact, this will be our cluster example. So, so the group is Z2 cross Z2, and so it has 4 elements, and actually the non-trivial projective representation is V of 0, 0 is the identity, V of 0, 1 is sigma x, V of 1, 0 is sigma z, and V of 1, 1 is sigma y. Okay, so that's the non-trivial projective representation of this group. And so you see, obviously the identity commutes with everything else, but that's all. None of the other elements of the projective representation commute with everything else. Yeah? Okay, so that's an example for a projective representation that's maximally non-commutative. And here I have attached the label maximally non-commutative to the projective representation, but it carries over to the corresponding cohomology class. So that's one term here, maximally non-commutative. So the other term we have to clarify is symmetry respecting basis. Okay, and so that just means that the post-measurement states, or the elements of the basis, they are invariant under the symmetry up to phases. Yeah, so up to phases, they are reproduced when the symmetry acts. And so in an example of our cluster state situation, so remember the symmetry was xi, so on and so forth. So the symmetry acts on a local system, a local spin by Pauli operator x or I. Yeah, and so the non-trivial constraint comes from when it acts by x. Yeah, and so we find that the symmetry, in that example, the symmetry respecting basis is the eigenbasis of the operator x. Because when x acts unitarily, all you get from these states are phases, but otherwise these states remain invariant. So that is what we mean by symmetry respecting basis. So the elements of the basis are element-wise invariant under symmetry action modulo phases. That's what that means. And now with all of this said, these people here from Sydney, they proved that the MPS matrices have this special structure. Okay, so where I is a label in the symmetry respecting basis. So this is not a basis independent statement. It refers to precisely that basis. Okay, that's what they showed. So now the implication is kind of immediate. So in graphical notation, this is what we just found. So this MPS matrix decomposes in a tensor product fashion where again, these guys here, they are constant across the face and they are determined by symmetry. So we know exactly what they are. And then there's a tensor factor B about which we know nothing. So we have absolutely no control over that thing. So now remember, when we think we think about measurement-based quantum computation in this MPS picture, the logical information lives on these virtual links. So now they are transformed by these matrices here. And so, well, so this a priori does not look so good because here you have absolutely no idea what you're doing. But then you have the tensor product. So the idea is, well, just don't use that subsystem. Use the logical subsystem. Here you know exactly what's going on. So you want to find a way of preparing product states, measure in the symmetry respecting basis, and then this is what's being applied. Here you have just these discrete sets of operators that happen. These are the byproduct operators of measurement-based quantum computation. You've seen them before. So here you know exactly what's going on, and here you know nothing. So you just don't use that system. So that's why it's called junk. So you're focusing on the system up here where you know everything. Okay, so that's the protocol. So you measure every site in the symmetry respect, in the symmetric basis or symmetry respecting basis. When you do that, that decomposition applies, and then only use the logical subsystem for transmission, and you keep track of the random byproduct operators, and if you want to, you can correct for them at the end. So that's the transmission protocol of Else and company. Yeah, and so the point is, because you have this decomposition in the entire phase, you have the wire in the entire phase. So that works independently of where you operate in the phase. Yeah, so underlying all of their reasoning is this group cohomology formalism. I want to simplify. No, I don't want to give you a complete theorem, a complete proof of the theorem, because yeah, we want to talk about more in this lecture, which is not going on for much longer. And so I thought I will simplify the proof a bit. So the first part of the proof will be general, but then at some point I'm switching to the Z2 cross Z2 cluster phase, just to make it a little bit simpler and so that we can make use of the stabilizer formalism. But I recommend to you that you read the general and original proof in that Else and company paper. Good, okay, so this is our starting point, the symmetry of the MPS tensors. Okay, so now, so the theorem was in the symmetry respecting basis, so we are contracting the tensor with that thing, with the basis states. Okay, and then on the right-hand side of this equality, we get this. And so now, rather than applying those unitaries to the tensor, we can apply them here to this post-measurement state. And because we are dealing with the symmetric basis, so this, so this is absorbed, this unitary is absorbed into that state modulo a phase, plus minus 1. Okay, good. So we're getting tensor component here with conjugated by the projective representation, and the equivalence holds modulo a phase. So that's a group character sitting right here. So in other terms, if you simplify it a little bit, so the tensor component AI is invariant under conjugation by the projective representation modulo a phase. Okay. So, and now, so the projective representation, the non-trivial projective representation that we have is the Pauli matrices. I mean, I'm not proving that, but people have shown that there's one non-trivial projective representation, and that's the Pauli matrices. So now, the Pauli matrices have dimension 2, and the dimension of this virtual leg here can be anything, really. And so we have the splitting of the projective representation into the Pauli operators and a tensored identity, a tensor factor of the identity. Okay, so over here we will get, it turns out we will get the logical system, here we will get the junk system. Now we wonder, okay, so if these are the symmetries, what kind of operators here can satisfy these relations. So these must be operators that commute or anti-commute with these projective representations. Yeah? Okay, so you want anti-commutation when this sign factor here is -1, and you want commutation when the sign factor is +1. So this is just worked out here as an example for a particular character, but I'm leaving it out. Maybe you can look up this detail if you want to later, but the point is to cancel these sign factors, you want commutation or anti-commutation here. These are Pauli operators, so that must be Pauli operators too. So you can follow, if you want to, this argument here for this particular case of character, but at that point maybe it costs you about the same amount of time to read the general proof in the Else and Company paper. So that concludes my discussion of symmetry-protected quantum wire. So the point of this whole thing was that it holds in the entire phase. Yeah, so it's the endpoint of it, and now we want to move to computation, and to kind of prepare for the transition, we have to discuss kind of where we stand. Okay, so far we have talked about measurement in a symmetry-respecting basis. The measurement in that basis allowed us to exploit this tensor, this factorization. Yeah, the factorization was good for us because it separated the logical system, which is under our control, from the junk over which we have no control whatsoever. Okay, so that was good about the symmetry-respecting basis, but yeah, it's just one basis, and what it does is wire, nothing but wire. And so, yeah, if I want to do something else, I will have to choose other measurement bases than symmetry-respecting, so I will have to use symmetry-breaking bases, but then I am losing this tensor product structure in general. And this means the logical subsystem will be mixed with the junk subsystem, and that will introduce logical decoherence. So it's kind of a choose your poison situation. So this is clearly very limited, but if I go beyond, then it looks like I'm screwed. Okay, and so that's the remaining problem to solve. We will indeed deviate in the measurement basis from the symmetry-respecting basis, but how do we deal with this logical decoherence? So that's the question that remains for computation. Okay, and so this is now the last part. Okay, so again there's a theorem. So in spatial dimension 1, the computational power of resource states for measurement-based quantum computation is uniform across symmetry-protected topological phases. And like it was the case for the phases themselves, the classification of the MBQC schemes, namely which gates you can do and what measurements you can perform, what logical measurements you can perform, are determined here by the symmetry itself and the group co-cycle. Yeah, so we want to show this constructively. Okay? So the task is deviate from the symmetry-protected basis without losing control. It looks like we're losing control. Yeah, maybe we are not. We need to discuss. So that's the task. And so there will be 3 computational primitives that we want to discuss. Maybe I will discuss the first 2. Maybe we can be a little light on logical measurement. Okay, so the first computational primitive is called oblivious wire. So this is mostly just wire. We will see in a moment. But it has a purpose for the computation. So what it does, it drives the junk subsystem to a fixed point state. Yeah? So that gives me some degree of controllability. So I don't know what that fixed point state is a priori, but I can make it. I can reset the junk system in a fixed quantum state if I want. Yeah? So that gives me a certain degree of control, certain degree of reproducibility, and that's what we will subsequently make use of as a first primitive. Okay, and so then, forget about the small rotation angle. We will look at large rotation angle too, but small angle first. Yeah, unitary operations basically. So that's the next thing, and if I have the time and the energy, then we will talk about measurements, but probably only briefly. So this is how we prove the theorem stated in a constructive way. I mean, we provide the computational scheme that gives this uniform power across the face. Okay, so let's get started. So here is oblivious wire. So oblivious wire is just pretty much the same like ordinary symmetry protected wire. But there's one difference. Okay, so remember, symmetry protected wire was just measure every system in the symmetric basis, and that just has the effect of teleporting the logical information across the chain. Okay, and so now the oblivious wire is just the same, except that after accumulating the byproduct, we are forgetting all these measurement outcomes. So we are erasing a lot of information. So oblivious wire is something that works on average. Yeah? So in every particular instance, it is just wire, but we are looking at it in an average fashion, so over many runs of the computation. And so here is what happens in a little bit more detail. So you measure every system in the symmetry respecting basis or protected basis, and we know that implements wire, and so it creates a new byte. So this measurement at hand creates a new byproduct operator, and we have old accumulated byproduct operator coming in from the left. Okay, so we propagate this through, yeah, so using the symmetry condition for our tensors, and so there is some symmetry action here to be absorbed in the state from the symmetric basis. Okay, so just gives us a phase. Yeah, and we have more accumulated byproduct operator thereafter. So it is the piece that was coming from the left and the new piece that was created from the measurement. And we bunch this together, and then the information we forget. I mean, we retain the product, but we forget what came from here and what was there before. Yeah, we only retain the information about the product. Yeah, so information is forgotten here, and that is essential. So we're averaging over all these various instances. Okay, so that's the procedure. And a useful way to think about it, even though, yeah, so there would be, I don't have the time to explain it fully. So remembering the accumulated byproduct operator is as good as correcting it. Yeah. So even though I'm not advocating for doing this, I mean, yeah, you could think about that way, that the byproduct operator is being corrected, and so that thing is gone, and the measurement outcomes you have forgotten anyway. If that helps you think about this. Okay, and so then what this procedure with after accounting of the overall byproduct operator, what it does is this. So this is so it acts then after taking account of the byproduct operator on the logical system. The action on the logical system is trivial, and what remains is the action on the junk system. And because of this forgetting of what the measurement outcome was, we are implementing this channel. So we have, yeah, so our density matrix of the junk system is conjugated by all of these junk operators, junk operator from the left, conjugated from the right, acting on the density matrix from both sides, and then summed over the basis state label. Yeah, so so after correcting for the byproduct, we are forgetting what we had, and that causes this averaging effect. Okay, and so that's a mix. That is an operation that typically makes density matrices more mixed, and it turns out, so without proof, if the ground state was unique, then this channel has a unique fixed point. Yeah, so if we apply this channel sufficiently open, we will approach this fixed point more and more. Okay, and that is the process that generates reproducible conditions on the junk subsystem. So we have a way of resetting the junk subsystem in a fixed state. We a priori do not know what that state is, but we can press a button and reset that subsystem. Good. So we are summarizing properties that we will need. So multiple application of this channel. So it's kind of oblivious wire of a certain length that drives the junk subsystem to the fixed point state. And then there's another property that is of interest, namely when we look at this object here. So this is the fixed point state conjugated from the left by some junk operator Bi, and from the right by the Hermitian adjoint of some junk operator Bj. So we take this thing, apply this channel many times, oblivious wire many times. So this gets us the fixed point state times some complex constant. So it has something, it has to, this constant is there because this operator didn't have to be trace 1 to begin with. And so, but so this thing, this limiting process will drive us to something proportional to the fixed point state. And this proportionality constant has this name here, is nu ij. And so if you think about it a little more, you can exchange I and j here, and then it turns out that this coefficient with the labels interchanged is just the complex conjugate. So the point is, well, this object here was something proportional to the fixed point state. And we'll use that later. Okay, now comes the second primitive. So here you see, so this is where the operation starts. So this is a small angle unitary. So there was previous oblivious wire. So that oblivious wire restored the tensor decomposition between logical subsystem and junk subsystem. And then you dare make a measurement of the symmetry respecting basis. So you measure in some symmetry breaking basis. So that will crush this tensor product structures, will entangle these two systems. So the factorization is gone. But thereafter you will apply more oblivious wire. So the oblivious wire will restore the factorization. So you will have the junk system in the fixed point state, tensor some logical state sigma prime. Typically a different logical state that you had to begin with because of this measurement here. But certainly the new logical state is some operator applied to the old logical state. So something is changing. And the question now is, what is that map? Okay, and so let's try to compute that in the time remaining. Okay, so the procedure is this. So you may have many levels here. So we are changing the first two. So they are basically what they used to be, but they have now a small admixture of the respective other one. And so that's governed by some rotation angle. So having the plus here and the minus here keeps the orthogonality, so we have still a basis. Okay, so they change, and all the others, if they are more, they remain what they were. So the action is here. Okay, so byproduct operation is as before, no change compared to anything we saw before. So we do this measurement, does some operation, and then we apply several rounds of oblivious wire to restore the factorization. Okay, so now let's see what this does. So A1 and A2, these would be the components of the tensor had you measured in the symmetry respecting basis. But now because of the changed basis, well, you have a linear combination of the two. So this is all for measurement outcome 1 prime, so the first. So post-measurement state is the state 1 prime we had here. So that's what we're now looking at. So this is the operation that you get. So for the parts, we have the nice decomposition by the Australian theorem. So we can take this thing out. And and so we have then the linear combination of these terms. So this is dominant, now has only a junk part. And so then we have C1 to the power minus 1 because of this C2. So we write this as C. This is still constant throughout the phase times another junk part. Okay, so this is the byproduct operator that's being taken care of by propagation. We don't need to think about it any further. So this is now the linear combination that we get. Yeah. Okay, so this is now a linear combination of these nice factorizing terms, but the sum is not typically factorizing. And so now, first thing that we discuss is what this does to this factored input state. So this, now we need to look at conjugation by this thing. So applied from the left and the complex conjugated from the right. So this will, we are multiplying from the left and the right, would give us 4 terms, but one is quadratic in the angle, and we just forget about that. Yeah, so we are only going to linear order. It gives us 3 terms. So we have the dominant term, d alpha to the 0th order. This is just b1 from the left and right. So logical system doesn't change. Fixed point state on the junk system is conjugated. Then come the terms to linear order in that rotation angle, assuming that's a small angle. And so now we have these funny conjugations from the left and right. So now B2 and B1 play a role. And you have C acting from the left and the right on the logical subsystem. So this is what we had. And now comes oblivious wire. So recall this identity. So oblivious wire applied to that is fixed point state times some number. And so now after you've applied oblivious wire, this transforms into that. These B's give you a number here, and all these B combinations give you other numbers. So the situation has now much simplified. So we have now fixed point state of the junk system here, fixed point system everywhere. So that was the purpose of oblivious wire. And now we have these funny combinations, constants, logical operation from the left and right, angle. Good. Okay. So we are almost done. So we have action from the left by C and C dagger from the right. And so we write this now as a commutator and anti-commutator term. And so sorry, there's now a tiny step missing, but maybe you can do this by yourself. So these 2 terms that we had, we now write as a commutator between action of stuff and the density matrix and an anti-commutator term. Okay, so this is a good sign because that looks like a unitary. So if you have a unitary with an infinitesimal rotation angle, the contribution that you get to linear order is a commutator term, exactly as we have it here. But you have this anti-commutator term that you do not want. And a nice thing now is that, remember, we did this just for outcome 1. If you do it now for the other outcome, then you find leading order, you get something similar but with a different constant. To linear order, you get the commutator term with the same sign and the anti-commutator term with the opposite sign. And so remember, we are forgetting measurement after byproduct operator taken care of. We forget about the outcome. So we are basically adding these 2 branches. And under that addition, the commutator term is amplified, anti-commutator term cancels. So it's really, to linear order, a unitary operation. That's the point. To linear order, we get a rotation about a small rotation angle. Yeah? And so the byproduct, the stuff that's constant across the face, appears here as a generator of rotation. So this was for infinitesimal rotation angles. And now we want to go to finite rotation angles. And so, yeah, so we've seen the deviations from unitarity. So at linear order in the rotation angle, there's no deviation from unitarity. So deviations from unitarity come up at second order at the earliest. And they do indeed come up in second order, as it turns out. And so the idea is to chop up a rotation about an angle phi into n rotations about an angle phi divided by n, yeah, and space these rotations apart by some distance. So then the error per individual rotation is phi squared over n squared. You have n such rotations, so the overall error is of order phi squared divided by n. So you make n large to get an arbitrarily small error. So you can make your error of order 1 over n by spending n amount of resources. Okay, and so that's it. Measurement gives nice pictures, but I'm not explaining it here. So this is the final result. So you can do unitaries generated by these operators, and you can measure these observables. Okay, so this is theorem 2 in long form. You apply this to the cluster phase. It turns out you can do these rotations, and you can do logical measurements of x and z. This is basically what we showed, but this is just for one logical qubit, so it doesn't stop there. If you want to go to computational universal phase, you have to go to dimension 2, spatial dimension 2, but that can be done. So you can have truly universal computational phases of matter in 2D, not just one qubit universal phases. That's it.